In lecture 21, we will study 3D modeling, which is the process of generating 3D models so that you can display them in your graphics software. So why do we need 3D modeling? So far, we have seen how to draw 3D models while mostly ignoring where they come from. Although I've shown you a real 3D face that was scanned, we didn't go into the depth of how to generate these models. Models need to come from somewhere. 3D models can come from three main sources. The first one is scanning real objects, similar to the 3D face that I showed you in a previous lecture. The second method, or the second source, is non-rigid deformation of real object scans. So this again involves scanning real objects. So both of them actually start from real objects and then give you different shapes. The third method is making synthetic models in 3D modeling softwares, such as computer-aided design softwares. For scanning real objects, many 3D scanners are available in the market. The price depends on the resolution of the scan. If you want to go high resolution, there is Minolta Vivid Scanner, the 3DMD Face Scanner, but these are expensive. If you want to scan in low resolution, you can use the Microsoft Kinect that comes with Xbox. The price is around $200. There's also similar devices from PrimeSense, RealSense, etc. However, to cover the complete 360 degrees of an object, we must scan the object from multiple directions. Now here you can see a statue of a dog is scanned from one direction, then from another one, then from a third one, and then from the other side, and so on. All these scans must be stitched together and then combined to form a single 3D object. Now, real scans need a lot of post-processing to remove noise, spikes, and to fill in holes. So no matter how many scans you get, if the shape of the object is complex, you will still end up with some holes that need to be covered. The second method is non-rigid deformation of linear models. Deformable models are made by aligning 3D models of many real objects. By changing the parameters of the deformable model, we get different 3D shapes that are linear combinations of the original objects. So you're still in the linear space spanned by the original objects. You've already seen how this works in Make Human. Make Human that is used in your project can vary the body shape, the skin color, and facial shape. This is because it has calculated these values from some scans, and now it is basically linearly interpolating from one scan to the other. Make Human also provides a small selection of clothing and a skeleton. Now let's look at computer-generated models. Scanning real objects and making deformable models are outside the scope of this unit. These are also complicated procedures that are not graphics related. We will focus only on how to generate 3D models using computer software alone. So they will not be real objects, they will be synthetic objects. One such example is inside Make Human, which can give you synthetic humans, and you don't have to go outside your software to get human scans. Another software that we can use is Blender itself. Blender includes many different tools used for different kinds of modeling. We'll focus only on a couple of fundamental techniques, such as subdivision surfaces and animation via skinning. So these are the two techniques that we'll focus on. In the project, we have given instructions how to import real animations from motion capture to Blender and animate a model. How can we easily model in 3D? 3D modeling can be tedious and time consuming. Even positioning a single point in 3D is tricky. Mice and displays are 2D devices. To use 2D devices to put a point in 3D is a tricky process. OpenGL is based mostly on drawing many triangles, and it is very time consuming to draw these triangles from scratch, and you may not still end up with the desired shape of the object. Placing each triangle individually is clearly not feasible. So how can we quickly and easily model 3D objects? Can we easily model natural shapes? We can quickly model blocky objects. As if you have played Minecraft, everything is blocky there and you can make new blocks in Minecraft. But most natural shapes aren't blocky. We can use pre-built common shapes such as spheres, cylinders, and ellipsoids, but again, natural shapes are not spheres and cylinders, and we cannot make every possible natural shape with a combination of these basic shapes. So can we generate shapes with many vertices by controlling just a few? Although we cannot place hundreds and thousands of vertices, we can move a few vertices around. So if we are able to control the shape of the remaining vertices with just moving a few vertices, this would be a feasible process. One such method is subdivision surface method, which can generate complicated shapes just by moving a few vertices or just by deciding a few vertices. Subdivision surface method is a method for producing smooth surfaces that can be adjusted easily. The idea is to specify a blocky surface. So you start from a blocky surface with a manageable number of faces, and then you calculate a smooth surface that roughly follows it. And this calculation is done automatically. The smoothing process needs to be predictable. It is related to earlier techniques such as NURBS, non-uniform rational B-splines, which also use a small number of control points. However, NURBS are computationally intensive, whereas subdivision surface method is more intuitive and it's more physically understandable. Subdivision surfaces is better for 3D modeling because it doesn't have a strict requirement such as points forming a grid of quadrilaterals, which is for other 3D modeling techniques. It is also useful to be able to edit the mesh at different levels of subdivision, which isn't possible with NURBS. So NURBS is not able to edit the mesh at different levels of subdivision, whereas subdivision surface method can perform this.